We have officially finished all the Calc 1 content, the volumes of revolution and cross sections and area of a plane region that we've just gone over. Officially finish up all of the Calc 1 content, all the content that would be on the AP Calculus AB exam. And from this point on, we're just going to be learning BC exam information. We already know some information that's only on the BC exam. For instance, Euler's method, it's only on the BC exam. L'Hopital's rule, surprisingly, is only on the BC exam. So we've already covered some BC content, but everything from this point on would only show up on the AP Calc BC exam. In the pre-cal review, we talked about parametric equations just really quickly, polar equations just really quickly. Remember, parametric equations can be used to describe motion that's not a function. If we have a curve in the plane that models what's happening to an object or a particle, we could talk about the horizontal behavior of that function, and that's what that might look like. This would be the horizontal behavior according to our parameter t. This function would model the vertical behavior of a function according to t. But when we graphed all the x values with their corresponding y values, when we graphed all of the xy points in the Cartesian coordinate plane, we definitely could get the graph of a function that would not pass the horizontal line test. So that's what this means, is not a function. These separately are functions. These separately would pass the vertical line test, but together there's a parameter in charge of what's happening to x and what's happening to y. I've had a previous student, when I taught at Ardmore, equated parametric equations, or the parameter, as t as independent variable. You have the independent variable. For us, that's always been x, and the dependent variable, for us, that's always been y. And so he learned it from a previous teacher that the independent variable was the driver and the dependent variable was the passenger in a car. And so, which I thought was a really good way to communicate to a pre-algebra student the difference between independent and dependent. And so parametrically, now the driver is the parameter t. T is not the only variable we can use as a parameter. You'll see that in a minute. And now there are two passengers. The passengers are x and y. X and y have to go where t drives them to. So I thought that was pretty good. Now, as far as bringing calculus into discussion, if the function f and the function g have derivatives at some given value of t, then the curve itself, all the xy points in the plane, would also have a derivative or a slope at that value of t. And we'll see that when we bring calculus into this discussion. But let's just talk pre-calculus here for a minute. And there are many times when we need to describe motion or a curve that is not a function. In other words, will not pass our vertical line test. We could do this by writing equations for our x coordinates and our y coordinates in terms of some third variable, some independent variable that's in the driver's seat. We usually see t, most often we're going to see t as the parameter, but theta could be the parameter, any variable could be the parameter. And so these functions are called parametric equations. And just remember, this is the horizontal activity that's going on in the plane. Here's the vertical activity that's going on in the plane according to t values that are the independent variable. So t is the parameter in this case. So let's look at and let's do some comparisons between rectangular equations, or what we're comfortable with as functions in the plane, and parametric equations. So parametric equations have three variables, and they can be used to represent a curve in the plane. This equation, this y in terms of x values, when x is the independent variable, we pick values of x, we plug them into this relationship, and we find the corresponding values of y, and we have all these xy points in the plane. So this equation can tell us where the object has been. But sometimes we need to know more than just where it's been. sometimes we need to know when it was at any given point. And so that's why we introduce that third variable, that independent variable. Now this information tells us not only where, but when our object or our particle was at any particular place in the plane. Now here are the equivalent parametric equations to that Cartesian equation that we saw in the last slide. Now, we'll never be asked to do this. We'll never be given some sort of Cartesian function in y and x and be asked to figure out the equivalent parametric equations. That's just not done on our test. What we're asked to do is to use calculus on these parametric equations. But sometimes we are asked to graph a parametric equation. So when you're asked to graph a parametric equation, remember old school. Go old school. Just like when you first learned to graph y of x functions, you would pick independent variable values, you would plug them into the function that you were given, and you would find the corresponding y values, and then you would plot those points in the plane. Well, we're going to do the same thing here. This is still the x and y plane, but now our independent variable is t, and x and y are the dependent variables. So graphically, we're really only going to see the dependent variable locations in the plane, but we do know when our particle or our object was at that physical location in the plane. All right, so that's all we've done here. I've picked 6 different values of t, plugged them correspondingly into these equations, these parametric equations, and found the corresponding x and y coordinates, and then plotted those points in the xy plane. And as you can see, even parametrically, the curve looks the same. Now we just have more information than we had before. All right, so you can go old school and graph a set of parametric equations in the xy plane. So let's work some examples before we introduce calculus here. This says find the Cartesian equation of the curve which have these parametric equations. A Cartesian equation is in y and x only. So here I have on A, x equals 2t minus 1 and y equals 8t squared plus 3. So if they want me to find the Cartesian equation of the curves, basically what they're asking me to do, and they could use this wording too, so make sure you know this, they're asking you to eliminate the parameter, get rid of t, find a direct relationship between x and y. Well, the process for doing that is to take one of your x or y functions, it doesn't matter which. Here there's less happening to t in the x function than there is in the y function. So I'm going to take the x function and I'm going to solve it for t. Instead of having x in terms of t, I want to wind up with t in terms of x. So I'm going to add 1 to both sides, that's going to leave me 2t, and then I'm going to divide both sides by 2. Now I have a function of t and x, and I can take this, if this is true that t equals this in x, then I can take that and substitute it into the y equation everywhere that I see a t. And I have successfully eliminated the parameter. There is the Cartesian equation for these parametric equations. So that's really all that it's asking you to do. Sometimes it's fairly straightforward to do. Sometimes it takes a little finesse. Here's one where I'm going to solve this for theta. Here is a set of parametric equations where the parameter is theta and not t. And you need to be comfortable with any parameter they throw in front of you. We never, never, never let notation trip us up. So I'm going to subtract 3 from both sides. That gives me 2 sine of theta. I'm going to divide both sides by 2. So sine of theta is x minus 3 divided by 2. Then I'm going to take the sine inverse of both sides. The sine inverse of sine just leaves me theta. And then I'm left with the sine inverse of x minus 3 over 2. Now I have put this parametric equation, instead of x in terms of theta, I have theta in terms of x. So same process as over here. I'm going to go pick up the y equation, and everywhere that there is a theta, I'm going to write this instead. If theta equals this, then everywhere I see theta, I should be able to write that expression. So this is the 2 times the cosine of the sine inverse of x minus 3 over 2 minus 5. So there are the Cartesian equations for the parametric equations that were given. Or they could ask you to eliminate the parameter, another way to ask you to do the process we've just done. Here's one where they ask you to sketch the curve with the parametric equations x equals 2t minus 1 and y equals t squared for t values from -4 to 4. Now be very careful, this is not x values from -4 to 4, it's t values from -4 to 4. So here's where we go old school. Remember, just pick some t values, plug them in, and find the corresponding y values. So here would be our t value, here's our x value, our y value, and these are the only coordinates we're actually going to sketch in the plane. But here's some t values. We'll pick -4, -3, -2, -1, 0, 1, 2, 3, 4. So let's plug those into the x function first. It's twice the t value minus 1. So 2 times -4 is -8, minus 1 is -9. 2 times -3 is -6, minus 1 is -7. And you could just go right on and fill that out. 2 times 1 is 2, minus 1 is 1, 4 minus 1 is 3, 6 minus 1 is 5, 8 minus 1 is 7. So it doesn't take that long to come up with the x coordinates. And now we'll do the same thing here. The y coordinate is just the t value squared. So these are going to be even easier to fill in fairly quickly. So it's not going to take that long to get your coordinates. And now we'll need to go from -9 to +7 along the x-axis. And we'll need to go, I'll probably just go from -9 to +9 along the y-axis. So 1, 2, 3, 4, 5, 6, 7. There's 7. And 1, 2, 3, 4, 5, 6. Need to erase that, give myself a little more space there. And we'll come all the way down here. So 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And 1, 2, 3, 4, 5, 6, 7, 8, 9. So -9, +9, -9, kind of give me an idea. So -9, 16, that point's going to be up here somewhere. -7, +9, there's that point. -5, 1, 2, 3, 4, 5, +4 is right around in there. -3, +1, and 0, 0, and we have 1, 1, and we have 3, 4, and we have 5, 9, and then we have 7, 16, which would be up here. And so from our t values, we're going to draw the direction as well. The direction of travel, and we just put these little arrows on it, from t equal -4 to t equal +4, all of our points are headed in this direction. So we would show whoever was following our work the direction of travel of this particle in the plane, because we don't really show t values that much. So there we are. That's how you would sketch the graph of a curve in the plane. I'll pick this up in the next video, so watch for that.